I'd like to look at how polynomial long division works by showing how it corresponds to an algebraic procedure for dividing improper fractions. Suppose I wanted to divide two polynomials f over g with a degree of f greater than or equal to the degree of g and g not equal to 0, since you can't divide by 0. I can write f as equal to a times x to the n plus k plus any remaining lower degree terms, and I could set that equal to a times x to the n plus k plus f sub l, where f sub l represents the lower degree terms if there are any. And then I could write g equal b times x to the n plus any lower degree terms and set that equal to b times x to the n plus g sub l, where g sub l represents the lower degree terms if there are any lower degree terms. The coefficients a and b are not equal to 0, and k is contained in z, so k is an integer but greater than or equal to 0. So if k is 0, these two have the same degree, and if k is larger than 0, f has higher degree than g. It should be clear that the degree of f sub l is smaller than the degree of f, since f sub l by definition just represents the lower degree terms in f, and that the degree of g sub l is smaller than the degree of g because g sub l represents any remaining lower degree terms in g. And this inequality will still hold even if one of the polynomials were just equal to a constant. For example, if f were just equal to a, so that f sub l were equal to 0. And that's because I'm using the convention that the degree of 0 is equal to minus infinity. So using these expressions for f and g, I can write the ratio f over g as a times x to the n plus k plus f sub l, using this, divided by g. And then what I can do is I can divide the leading term in f by the leading term in g. And if I do that, the n's will cancel out and I'll have a over b. It'll give me a over b times x to the k. So that means I can write the leading term in f, a times x to the n plus k, is equal to this multiplier over here times this leading term in g over here. So I rewrite the leading term in f like this, and now what I can do is I can take that multiplier and I can multiply it by the remaining terms in g and add it on over here. Now in order to compensate for adding that on, I have to subtract it off over here, and then I just bring down the remaining stuff, the f sub l. And if I do that, then what I can do is I can take these two terms, factor out the multiplier, and then I'll get the g back again. So if I divide this by g, the g's will cancel here and here, and I'll just get the multiplier over here, and I'll get the remaining stuff here over g. So what I've done is I've rewritten the original fraction f over g as one term in the quotient plus a modified numerator divided by g. And the nice thing about this is that the degree of f sub m, the modified numerator, will be less than the degree of f, the original numerator. And that's because f sub m is equal to f sub l minus a over b times x to the k times g sub l. And the degree of this term and the degree of this term are both less than the degree of f. And the degree of f sub m has to be less than the degree of this or the degree of this. That this holds is clear just by looking at this expression for f, since f sub l represents all the lower degree terms in f. The degree of f sub l is clearly smaller than the degree of f. And then if I look at the expression for g, it should be clear that the degree of g sub l is smaller than the degree of this leading term over here, since by definition g sub l is all the lower degree terms. Now if I take this expression over here, this inequality, and I multiply the g sub l on this side and the b times x to the n on this side, both by the same factor, a over b times x to the k, what I'm going to be doing is boosting the degree of both sides by k. So since I'm boosting the degree of both sides by the same amount, the inequality will still hold. So this will be smaller than this, and over here the b's will cancel, and I'll have an a from here, and then I can combine the exponents over here and have x to the n plus k, and this here is just the leading degree, is just the leading term in f. So the degree in this is the same as the degree in f. So the degree of this term over here, from here, is smaller than the degree of f. And the reason this happens is that if you go back and look at the procedure, this times this is the leading degree term and is the leading term in f. So this times this is the highest degree term in the numerator. And when I divide by g, this and this cancels, and I knock this term out of the numerator, leaving only lower degree terms over here. So if I carry out this procedure and the degree of f sub m is still greater than or equal to the degree of g, what I can do is just repeat the procedure until eventually I get a modified numerator whose degree is smaller than the degree of g. And in that case, I'll have this situation over here, and the final modified numerator will just be the remainder, since its degree will be less than the degree of g. And I'd like to do an example of this procedure using this fraction over here. So what I do is I take the leading term in the numerator over here and divide it by the leading term in the denominator over here. That's this over this, and that gives me 2x squared. So I can write this leading term in f over here as 2x squared times x. So I rewrite this as this. And then what I do is I take the multiplier here, 2x squared, and I multiply it by the remaining stuff in the denominator. And in that case, that's just 2, so I get 2x squared times 2. And this term is 4x squared. So to compensate for adding that term, I just subtract the 4x squared. Then I bring down the remaining stuff in the numerator, the x squared minus 1. And then what I can do is I can factor out this multiplier over here from these two terms and get 2x squared times x plus 2. And then just combine and bring down these remaining terms over here. Then when I do the division, this will cancel with this, and I'll get the first term in the quotient, 2x squared, and this stuff over here will become the modified numerator. So this ratio of the leading terms becomes the first term in the quotient. And you can see from this that the degree of the modified numerator is less than the degree of the original numerator. And if you look at this again, this is degree 2 and this is degree 1. So the modified numerator, so this term over here, this fraction over here, is still an improper fraction. So what you can do is just take this fraction over here and repeat the procedure. So you take the minus 3x squared and you divide it by x over here, the leading term here divided by the leading term there, and you get minus 3x. So I can rewrite the minus 3x squared as minus 3x times x. So I rewrite this like this. Then I take the multiplier minus 3x and I multiply it by the remaining stuff in g, the g sub l, which is just 2 here. Now I've added the term, I've added this term, and this term is the same as minus 6x, so I have to subtract the minus 6x. So minus 6x is plus 6x. And then I just bring down the remaining term in the numerator, which is just minus 1. Then I can factor out the two multipliers over here and get minus 3x times x plus 2, bring down this term, and then when I do the division, these two terms cancel, and I get the minus 3x as the next term in the quotient, and the 6x minus 1 is the modified numerator. And again, you can see that the degree of this is less than the degree of this. But the degree of this is 1 and the degree of this is 1. So this is still an improper fraction, so you can apply the procedure one more time on this fraction over here. So you take the leading term here, the 6x, and the leading term here, the x, you divide them and you get the multiplier 6. So you can rewrite the 6x as 6 times x. So I just rewrite this like this. I take the multiplier 6 and I multiply it by the remaining stuff in the denominator, just the 2. So I've added on 6 times 2, which is 12. So I subtract off a 12, and then I just bring down the remaining minus 1 in the numerator. And then I can factor out the multiplier 6 and get g back over here. Combine these two terms, get minus 13. And then when I do the division, this cancels with this. So I get the multiplier 6 as the next term in the quotient. And I get the minus 13 as the modified numerator. So if you look at minus 13, that's of degree 0, which is less than the degree of this over here, which is of degree 1. So again, the modified numerator is less than the numerator I started with. Now, minus 13 over x plus 2 is a proper fraction. So, since the degree of this is less than the degree of this, the procedure ends here. And the minus 13 is the remainder. So if I collect all those terms, here's the original fraction over here, and that's equal to this. So I get 2x squared plus this, but this is equal to this, which is equal to the minus 3x squared plus this fraction. So I'll have a minus 3x plus this fraction. So I have minus 3x here, and this fraction here is equal to all this. So I get a 6 plus minus 13 over x plus 2. And this is the quotient, and this is the remainder. Now, if I were going to do this procedure using polynomial long division, what I would do is I would take the first term, 2x cubed, and divide it by x, and I'd get 2x squared. And that corresponds to dividing this by this. So I have the 2x cubed over x gives me 2x squared. And after some algebra and dividing over here, the 2x squared becomes the first term of the quotient. And then the next step in the polynomial long division would be multiplying this times this, and that would give me the 2x cubed back again. And then the 2x squared times the 2, which would give me 4x squared. So that step reproduces these two terms over here. And then what you do is you subtract off those terms. So I'd have a 2x cubed times a minus sign, which gives me minus 2x cubed. Then added to that, those terms will cancel. And that corresponds to doing the division over here and knocking this leading term, 2x cubed, out of the numerator, producing this first term in the quotient. And then I have to subtract off this term, so I'll have 4x squared times the minus sign is minus 4x squared. And then when I combine it with the remaining stuff over here, I get minus 3x squared plus 0, which is just a placeholder, minus 1. And subtracting that off and getting this corresponds to these terms over here, with this term here subtracted from the numerator. And then you can combine these terms and bring them over here, and after the division, those terms become the new modified numerator, which corresponds to this. So from here to here is just one iteration of the long division, and that corresponds to the first iteration of this procedure over here. And then the next step is to repeat the process and divide this x into this minus 3x squared, and that'll give you minus 3x. And that corresponds to dividing this term by this term over here and getting the minus 3x as the multiplier, which after some algebra becomes the first term and becomes the next term in the quotient. Then you take the new term in the quotient, the minus 3x, and multiply it by these terms, and you get the minus 3x squared back again. And then this times this gives you minus 6x. So you've reproduced these two terms in the numerator over here. Then you subtract off these terms, so you have a minus 3x squared. Let me just fix that. You have minus 3x squared times a minus sign, which is plus 3x squared, combined with this. Those two terms cancel, which corresponds to this division over here when you knock the minus 3x squared out of the numerator. Then you have to subtract off this term, so you have a minus 6x times the minus sign is plus 6x, combined with these terms gives you 6x minus 1, and that corresponds to this subtracted term combined with the remaining term here, which after some algebra just becomes the next modified numerator. So this is the second iteration of the long division process, and that corresponds to this iteration of this algebraic process. So then what you do is you repeat the procedure. You divide this x into the 6x over here, and you get 6. And that corresponds to dividing this 6x by this x. Over here, which gives me the multiplier 6, which after some algebraic manipulation becomes the final term in the quotient, 6. And then you multiply this back onto these terms, so you get 6x back again. And then 6 times 2 is 12. So you reproduce the first two terms over here, and then you have to subtract these off. So you have 6x times a minus sign, which is minus 6x, plus 6x cancels, which corresponds to this division, knocking the 6x out of the numerator over here. And then you have to subtract this term, so you have 12 times a minus sign is minus 12, plus minus 1 is minus 13. And that corresponds to these two terms over here. You combine these two, you get minus 13, and after the division, the minus 13 becomes the remainder. So this is the final iteration of the long division, and that corresponds to this final iteration of the this algebraic procedure. So the long division reproduces the quotient over here and gives you the same remainder over here.